On March 20, 2025, engineers at NASA's Jet Propulsion Laboratory sat around their screens and waited. The day before, they had sent a sequence of commands to a spacecraft more than 15 billion miles from Earth, traveling through interstellar space at roughly 35,000 miles per hour. The commands had taken more than 23 hours to reach Voyager 1. And now the engineers had to wait another 23 hours for the response. Then the data arrived. Something unexpected was happening. The temperature of a set of thrusters that had been considered dead and unusable since 2004 was rising. Within minutes, the numbers continued climbing. The thrusters were alive. Voyager 1 had just received one of the most remarkable remote repairs in the history of space exploration. The mission's propulsion team lead, Todd Barber, described the thrusters as having been considered dead. Then came the line that perfectly captured what had happened: another miracle save for Voyager. But this was not simply a story about bringing old thrusters back to life. It was the beginning of another extraordinary chapter in the survival of Voyager 1. The spacecraft has faced failing thrusters, shrinking power reserves, communication problems, instrument shutdowns, and increasingly difficult engineering challenges. And somehow, it continues. Voyager 1 launched on September 5, 1977. It was designed for a mission lasting about 5 years, primarily to study Jupiter and Saturn. That mission succeeded far beyond expectations. The spacecraft photographed distant worlds, transformed our understanding of the outer planets, and then kept going. It kept going for another decade. Then another. In 2012, Voyager 1 crossed the heliopause and entered interstellar space, becoming the first human-made spacecraft to reach the space between the stars. Nearly half a century after launch, it is still traveling outward. Its signal now takes more than 23 hours to reach Earth. Every command NASA sends requires patience. Every response requires even more. And that makes every repair incredibly difficult. The first major crisis of this recent chapter involved Voyager 1's roll control thrusters. These thrusters help keep the spacecraft correctly oriented so its antenna remains pointed toward Earth. Without that control, Voyager could slowly rotate away from Earth, weakening the signal until communication eventually became impossible. The primary roll control thrusters had stopped functioning in 2004. For more than 2 decades, engineers relied on a backup system. But by 2025, those backup thrusters were developing their own problem. Residue was accumulating inside their narrow fuel tubes, restricting the flow of propellant. Engineers estimated that the backup thrusters might eventually become unusable. That created a terrifying possibility. If the backups failed while the primary system remained dead, Voyager 1 could lose its ability to maintain its orientation. The antenna would drift. Communication could be lost. The mission could effectively end. So engineers went back through decades of documentation, old wiring diagrams, telemetry records, and engineering data from a spacecraft designed in the 1970s. They began asking a simple question. What if the primary thrusters had not actually been destroyed? What if their heaters had simply lost power because of an electrical control problem? If that was true, there might be a way to restore power to the heaters and bring the old thrusters back. But the plan was extremely risky. Those thrusters had been cold for more than 20 years. If Voyager's attitude changed while the heaters were still warming up, its automatic control system could command the thrusters to fire. Firing a cold thruster could potentially damage the system. The timing had to be precise. The heaters needed to become operational before an automatic correction could be triggered. And there was another problem. NASA had a limited window to attempt the repair because the Deep Space Network antenna in Canberra was scheduled for a major upgrade. Once that antenna went offline, engineers would have far fewer opportunities to communicate with Voyager 1. So the command sequence was sent. The engineers waited. More than 23 hours later, the commands reached Voyager. Then came another agonizing wait. Finally, the telemetry arrived. The heater temperatures were rising. The experiment had worked. The primary roll control thrusters, which had been considered dead since 2004, had been brought back online from more than 15 billion miles away. It was an incredible engineering victory. But Voyager was not finished testing the people trying to keep it alive. In 2026, another problem emerged. During a planned spacecraft maneuver, engineers noticed an unexpected change in Voyager 1's available electrical power. The spacecraft was not suddenly dead. But its shrinking power budget was becoming even more difficult to manage. Voyager's radioisotope thermoelectric generators produce electricity from the heat released by decaying plutonium. That power supply has been declining continuously since launch. Every year, there is less electricity available. And on Voyager, every watt matters. Eventually, NASA had to make a difficult decision. An instrument had to be switched off to protect the spacecraft's most critical systems. The low-energy charged particle experiment was shut down so that the remaining power could be used elsewhere. It was not a decision the mission team wanted to make. But Voyager's survival depends on making choices that would have seemed unimaginable during its original mission. The spacecraft launched with a suite of scientific instruments. Decades later, only a small number remain operational. And even those remaining instruments are precious. The magnetometer continues measuring the magnetic environment around Voyager. The plasma wave subsystem continues detecting signals from the interstellar plasma surrounding the spacecraft. These measurements are extraordinary because Voyager is not observing interstellar space from millions of miles away. It is inside it. There is a huge difference between observing an environment remotely and actually measuring it from within. Voyager is giving scientists direct measurements from a region of space no other spacecraft has ever explored in the same way. When Voyager crossed the heliopause, scientists discovered that the transition into interstellar space was more complicated than simple models had suggested. The magnetic environment, plasma conditions, and boundary itself revealed details that could not have been fully understood from Earth. And Voyager is still moving farther outward. Every measurement adds another piece to our understanding of the space between stars. That is why every functioning instrument matters. Once an instrument is shut down permanently, that particular stream of measurements may be lost for decades. And that brings us to another remarkable engineering effort. NASA has been developing ways to reduce Voyager's power consumption without sacrificing as much science. One of the most ambitious procedures has been nicknamed the Big Bang. The name has nothing to do with the origin of the universe. It refers to a coordinated power management operation in which multiple systems are switched and reconfigured in a carefully synchronized sequence. The procedure was first tested on Voyager 2. That test was crucial because Voyager 2 is the twin of Voyager 1 and faces the same fundamental problem. Its power supply is slowly fading. The challenge is not simply electrical. Voyager's electronics also need to stay warm. In the extremely cold environment of interstellar space, some components must remain above minimum operating temperatures. A badly timed power reduction could therefore do more than turn off an instrument. It could permanently damage hardware. That is why the procedure had to be carefully coordinated. If the technique can be successfully applied to Voyager 1, it could potentially extend the spacecraft's scientific life and preserve valuable instruments for longer. That is the real battle happening right now. NASA cannot replace Voyager 1. No new spacecraft is currently sitting in a hangar waiting to take over its exact role. There is no backup machine already positioned in interstellar space. Every instrument that stops working represents a unique scientific capability disappearing forever. And Voyager is getting farther away every single day.